So this course will be on effective field theories, which is objectively a very broad topic with applications in many different fields. And in fact, a few years ago, I went to a conference in Paris, effective field theories. So there were people, the title was effective field theories, and there were people working on collider physics, on cosmology, on even on certain things related to condensed matter, gravity, etc. And I was very happy. I thought, okay, finally, because I'm an expert in effective field theories, I will understand all these topics because they're all expressed in the same language. And as a matter of fact, I didn't understand anything at this conference. So you have this feeling that effective field theory is something universal and the rules are always the same. It's just the essence that changes, but it's not entirely true. And so when thinking about what I can come here and teach, I kept this in mind. And initially, my goal was to make you an expert in all these fields, but it's not going to happen. But so the goal of these lectures is mostly to give you a taste of effective field theories in slightly different domains, so that you can learn it from a high-energy physics perspective, which is at the core of this course. But then you can also keep in mind what changes when you move to a slightly different topic. And so let me maybe start with telling what these effective field theories are. So the slogan of these effective field theories is that they are almost equal to quantum field theory. So if you know quantum field theory, somehow probably you already know to some extent what an effective field theory is. And there is a picture that maybe helps you organizing what the differences are, which it's a picture you find in many talks related to formal aspect of quantum field theory, which is the idea that we organize nature on this line where on the highest part you have high energies, small distances, what I call the UV, and down here instead you have the IR, small energies, longer distances. And the idea is that nature of the things that we want to study is a flow across energies that relates these two regimes, okay? So in quantum field theory, you have the ambition of understanding this entire picture at one go, okay? So we have the photon, neutrinos, whatever, the up quark, etc., etc. We have the Higgs boson, the top quark, and God knows what else extra dimensions deliver for us, and so on, and eventually you arrive to the Planck scale, and there are more states. So in quantum field theory, somehow I had this idea that you're going to capture everything, okay? Now, effective field theory has a similar picture, but is less ambitious. It basically aims at describing only a part of this flow. So it only aims at understanding physics below a certain energy, a certain mass gap that I will call M, okay? So the reason why this is good has to do with the fact that this picture, which is very attractive and intriguing, it doesn't always work for us. For instance, in gravity, we don't know what the UV is, right? We can understand the theory of gravity. It's very helpful at the distance scales that we need it, but still we don't know the UV. So this picture of an entire flow doesn't happen. And similarly, as we will see today, QCD that Julia has introduced already to you has a problem that although it's a very nice and perturbative theory at high energies, it is associated to the strong coupling alpha S. And strong coupling alpha S, when it gets to a certain scale, lambda QCD of about 1 GeV, this coupling becomes of order 1 in certain units and is no longer perturbative. Perturbativity is at the core of Julia's course, but the fact that at some energy scales it becomes large, it means that you can indeed talk about QCD here, but when you get here, something happens, and somehow you can no longer compute and predict what happens when you go to lower energies. So from QCD, you don't have direct access to this. Yet, effective field theories, as we will see today, will allow you to cut this picture in two, having one part in which you think about QCD and having another part in which you effectively think about the pions and particles that originate from the confinement of quantum chromodynamics, okay? So gravity and QCD are two good examples in which you don't want to study the whole pictures at all energies, but still it is useful to focus on a limited regime in energies and distances, okay? So the advantages of these effective field theories is that they are more pragmatic, they are simpler because you see we have a few states here, but then we don't need to describe the others above. So in that sense, there's less states to care about. But the kind of drawback of these advantages is that the Lagrangian is infinite. It's not a compact, beautiful formula like the one we saw this morning for QCD. Lagrangian of the theories that live down here have an infinite series of terms in it. So let me give you an example that maybe some of you have already seen, but I think it's always good to go back to this, which is a simpler version, so not with all these states, which we don't need. We only put two states, a state that I call phi, small phi, and has mass m that, for simplicity, I will take to 0, okay? And then there is another state, which I'll call big phi, and has a mass big M, okay? And so the Lagrangian describing the quantum field theory with these two states is, I'm giving it to you exactly in the same way you receive the QCD Lagrangian. Take this one. So we have kinetic terms for the small guy and the big guy. But anyway, tell me, I'm not a very good handwriter, I know it, but I think it's good. You will learn more. You put more energy into reading and it will stick. Right, and there is a mass term, mig mass for the big guy, okay? The other one, we put it to 0, and then we have an interaction, which is, I'll write it here as minus mu over 2 big phi squared. So the interaction is big phi, small phi, okay? So this is the QFT that I'm giving you. And now it turns out, so in this QFT, we can compute things, and let me focus on a specific observable, which is the scattering of two small guys here, mediated by a heavy guy, okay? So the amplitude, I'm sure you have already seen this thing in some form, is written as, well, I'll write it here, mu squared, because we have a mu here and a mu here, okay? And then there is a propagator at mass big M, and you have the same diagram in 3 different channels, so the T and the U channel, okay? So you add these 3 guys, and this is your amplitude, okay? This amplitude at small energies, you can expand it, and it gives you 3 over m squared mu square plus it's an infinitely long expansion in powers of this STU, which, by the way, if you're not familiar with it, S is the kinematic energy that enters here. Here is pi1 plus p2 squared, written in a Lorentz invariant form. And similarly, you have T, which is p3 minus p1 squared, and U is equal to p4 minus p1 squared, okay? Good, so what then? Well, the reason I'm showing you the expanded version is the fact that there exists a theory, an effective theory, that is written entirely in terms of the small phi, contrary to this one that has the light and the heavy. And this theory takes this form. Has a kinetic term for our guy, right? And then it has a series of interactions that you can write like this. Good. Now I have a question for you. We're all a bit shy, and I'm trying to compensate for this with the following tool. How do I get this thing to work? On, maybe? Okay, it's now on. It's turning on. Okay, so let me see. It's turning on. Okay, so the thing I'm going to do is the following. I'm going to write a question on the board, but you don't have to lift your hand and answer. You take your mobile, you scan, there is a thing there. Sorry, let me launch before I activate, clear. Okay. Do you see it? All right, so you scan this thing. Well, let me ask the question first. So the question is, the G1 there is equal to so which one of these is the correct answer, okay? So take a few moments to compute it, get the factors right. I'm not the one that gets them right normally, but this is the time you should. And in a minute, we will look at what you guys answered. So, well, pick the first three, right? It's, I can give you more. I can give you more. 0, 1, infinity, right, go. Well, there is no, unfortunately, it's quite primitive. No, with the G1 here, sorry. Yeah, sorry. The G1 here, they take some value. The question is, what does the G1 need to be in order, yeah, sorry, I actually didn't say the entire question. So what the Gn, and in this case, the G1 needs to be in order to reproduce the same value that we get in the full theory in the expanded form, okay? So we want the UV theory on this observable to be equivalent to this effective field theory, and there is some matching that we have to do between those coefficients and the coefficients that we computed here in the full QFT. We're missing an M. Maybe not, maybe it's correct, who knows? I mean, of course, some of these answers are wrong, right? So if one is missing an M. Right, I cannot leave you the full day, otherwise we will not get anywhere, but it's good that you even talk just 1 minute about this. So let's see the answer. All right, okay, well, not many of you responded yet. Well, it's moving. Don't be biased now by the majority. You see the bias. Vroom! Now suddenly they see the statistics. It all goes on this. It's correct, okay? So we can even show it on percentage, but you see it on these bars, right? So the correct answer is this. And the way you see it, well, you can compute it explicitly, but we got to get a factor of 8 out. And so the question is, when you compute an amplitude with this guy, right, what happens? Well, the Feynman rule of this box is going to give you a pi plus pj with a minus sign. Feynman rules, not Francesco Riva. They give you this minus pi plus pj squared, okay? This is the Feynman rule associated with the box, and when you compute it, right, you pick up a factor of 2 factorial, because you have to contract this with the 2 initial legs. You pick up another 2 factorial from this guy, and then you have to put in all the kinematic invariants, which would be, sorry, this is, by the way, we will have P1 plus P2 squared plus P3 plus P4 squared plus the others. But what you see is that this is equal to S, I told you there. And but for momentum conservation, this is also equal to S, okay? So from this, you pick up a factor of 2S, 2, 2, 2, it gives you the 8 that we have here, okay? Good, so enough for the question. We'll come back to another one later to keep you awake. So the message, I'll erase also this, maybe. Well, the message is that these 2 theories they reproduce the same observables at low energy if the Gn, you can compute all of them, are equal to -1 to the power of n, and then mu squared divided by big M to the 2 plus 2n, okay? So with these theories, the EFT at low energies, we have that the EFT is equal to the full QFT, okay? Computed from this observable here, okay? Yes? Why the 2 factorial? Okay, good. So because we have, when we compute this amplitude, right, we have the 2 initial states that has P1, P2. So in your amplitude formula, you have P1 and P2. And then you have to contract this thing with these guys, okay, to compute the amplitude. And here, which of these 2 phi's you choose? And you have 2 choices. Well, 2 factorial, sorry, but it's 2. Basically, these are 2 guys. We can call it phi, phi. So I can do the first particle with the first guy, and then the second particle with the second guy. Okay, so you get a factor of 2 from this, and the same on the other side. Okay. So let me erase this. Hopefully you're fast enough to copy. Yes.
If I were to do the one loop matching,
Good.
and I would have that the scalar in the infrared as a mass.
Right. So the masslessness here was an easy way out to have one less line. But you're right.
So
yeah.
you, in some way, how do you deal with that?
No. In that sense, I mean, well, it would have a mass. Meaning, imagine that we tuned. This is a purely infrared accessible piece of information, the mass of the guy. So we fix it here. I fix it to 0. You say it when you renormalize it, it gets another piece. Kaustub would not agree. I'll just put it to 0 and leave it there. But you're right. There's the whole hierarchy problem. But for now, this is fine-tuning. It's like just a phenomenological tool. So you match to what you observe.
Okay.
And thank you. Yeah. Don't hesitate to interrupt. Good. So we have this beautiful matching. But now we see that this theory is actually better. Let me put a heart here, because imagine that I add another guy here with a mass big M prime and a coupling in the Lagrangian given by mu prime, phi prime, phi square. Just another guy of the same type, okay? Now, sorry, I'm not handling very well these 5 boards here. I had a good plan of being well organized, but let's see where it goes. So if I now, I can write this new theory in the same form. I just change the values of Gn. So the theory with a small phi, the big phi and the big phi prime, matches to the theory with just phi, with the Gn now given by -1 to the n, and I have the 2 terms to add, mu square over m to the 2n plus 2, and the new guy, mu prime square divided by m prime 2n plus 2, okay? So good. Another theory, just moving the coefficients, and you can go on, right? You can put as much complexity as you want. This guy remains the same, hence the heart there, okay? So it's a good, how do you say, scaffolding for welcoming many UV completions, okay? And so the point is that this thing with G undefined it captures many UV theories, okay? And more generally, we write effective field theory in exactly a form like the one you see there, sum of some coefficients, and then some operators, which are operators of the form m derivatives and n fields distributed somehow, okay? Similarly to here. Here we had 4 fields and, well, 2n derivatives, but in general you can write a generic effective field theory in this form, okay? And these are operators in terms of the light fields. Light as in massless, not light, okay? Just in case. Later we will have light as well, but it's not here. So let me give you a list more explicitly than the one we have there. I'll put it here, then it will be useful. For instance, we have phi square, we have phi cube, we have phi to the 4, we have well, we had the guy written there, 5 square box, phi squared. We have delta phi to the 4. I mean, I can go on forever here, of course. There are infinitely many terms, but I'm just putting a few that later will tell us something, and so on, okay? So these are operators that appear in an effective field theory with coefficients that are not defined yet, okay? Good, so we have a first sense of what effective field theories are, but what the hell do you do with these effective field theories? The problem is that in physics, we don't want just to build theories, we want predictive theories. So predictive effective field theories is a subclass of this junk here, because if we put all the operators, then there is no prediction. Just because if you put everything, there is nothing. You see what I mean? There is no, there are too many things. We will see actually a very good example in a couple of minutes. Yes? Ah, the light. Turn on the light. Yeah, I will tell you when turning off. Okay, good. So, and we have prediction. So prediction, when we have less operators, okay? And so less operators, it's a concept that goes one-to-one in hand with the idea of symmetry. And here, if you are slightly puzzled by this, well, Kaustub mentioned something this morning, this hierarchy problem. Hierarchy problem is an instance in which you have an operator, the mass of the Higgs, or the scalar in general, that is not forbidden by symmetry, and then you get this large contribution from renormalization in the underlying theory. Here is the same. If you want to put some operator to 0, and you think you're clever, and you say, let's take the C10 to 0, right? Then what happens is that you move along energies, okay? And these coefficients are like couplings. They change with energy. The renormalization group, renormalization flow within theories, right? And so something that was equal to 0 suddenly becomes different from 0. So this is not a predictive thing. So you think you got rid of some operators, but it's not something stable. Instead, symmetries, they are renormalization invariant statements, okay? If you have a symmetry associated with the absence of an operator, then this coefficient will remain 0 when you move across energies, okay? So we are piling up ingredients for our effective field theory. Are there more colors? Or yeah, we have Brazil that it's full of things, and then we have only purple and, okay. Yes, this is a weird violet, but okay, anyway, new color. So the first ingredient, the first defining ingredient of an EFT is the particles, the light fields. And the second one is the symmetries, okay? Second ingredient. Okay? So what do I mean with symmetries? Let me give you a few examples. So I come back to this list here that we did before, where I just wrote down a few operators of the many that you can write down. And let me give you a few symmetries, okay? So one possible symmetry is phi that goes to minus phi, okay? I'll write them all here. Another one is phi that goes to phi plus a constant. And another one is phi that goes to phi plus a constant plus a b times x, so a space-dependent thing. And let's look who of these guys is allowed. Well, okay, I could ask you a question, but yeah, look at them, think a second. In the meanwhile, I'll tell you who's not allowed. So phi cube, not allowed by the symmetry. Anything odd is not allowed. So even this guy here, there are 1, 2, 3 fields, not allowed, okay? This one is even better. The phi shifts by a constant. So in the Lagrangian, exactly. So if you don't have derivatives, here you're gone, okay? So goodbye. What about him? Kill it. Okay, good. Him? This is like Rome. Good, we leave it, and that guy as well, we leave it. This one is even harder, so it kills everybody. It even kills this guy, because you see, when the bx leaves your constant on the delta, it turns out that it's okay with this last term, okay? You might be wondering, but we don't have enough delta. We're coming back to this later. It's a bit of a special class of symmetries. It turns out that this shifts up to a total derivative term. We're going to see it later. By the way, these particles here, this is a Goldstone boson of, again, we're going to see it today, like a pion, and this is called a Galileon. It's going to come back again tomorrow or the day after, okay? Good, so, null as in not zero, you mean, not null, yeah? Right. Well, this is meant to be for generic things. It's like a shift that is, because it's a parameter in the group, like C but yeah, maybe there is a group defined by null Bs, still a continuous class. It would be nice to think. Then this is automatically, this one. Yeah, well, we can think what the cosset of there. Yeah, there is a whole avenue for cosset constructors here. Okay, good. So we have two ingredients. We've seen how symmetries kills some of these guys. And before getting to the third ingredient, let me just tell you that these operators, OIs, they change importance in their flow. In the energy flow. So we can think of the energy flow as a rescaling x going to x over lambda, where lambda going to infinity, we're zooming on smaller things. So lambda infinity is the UV, and instead lambda going to 0 is the IR, okay? So by this rescaling, you move from high energies to low energies. And now, you can follow in the action. The action is a number, is integrated the Lagrangian over d dimensions. So this part will go like 1 over lambda to the d. The Lagrangian goes like lambda to the d to make this invariant under our transformation. And so let's follow this thing. How does the operator move around? Well, we are in a quantum field theory taught as a weakly coupled theory. So where you expand around the free theory, the kinetic term, right? This is what we always do when we do perturbation theories. Effective field theories are, at least the ones that I will talk about, fall in this class. So we want to study a free theory plus some interactions. So let's look at the term that dominates the particle dynamics, which is the kinetic term, okay? So in the kinetic term, we use delta phi square to read the phi scaling. And phi goes to lambda to the d halves minus 1, just because in the kinetic term we have d phi square. This must go like lambda to the d. The derivatives go like lambda, and so we're d halves minus 1, okay? Nodding all the way back. Still nodding, okay, good. So, right, then means that an operator of that form there, so an operator that goes like m derivative and phi and n phi's will go like lambda to the delta, and this delta is equal to m plus n times d halves minus n. D is the dimensions of space-time, so I mean 4 for us. Well, I just keep generally so that this formula doesn't look too miserable, okay? Okay, so now we can tell when we move to longer or shorter distances what happens to an operator. So if delta is smaller than d, then when we go to low energies in the infrared, the operator becomes bigger, okay? So delta smaller than d is relevant, we call it, relevant in the infrared, in the IR. Instead, when delta is bigger than d, is irrelevant. In the IR, okay? And the limiting case, delta equal t, is marginal. Okay? So this is how we follow things. And if you think this is abstract, maybe let's look at an example that we saw before when we computed the amplitude for 2-to-2 scattering in this theory and in the effective field theory, okay? Well, let me use the amplitude square. It's a bit easy. So S times the cross-section as a function of energy. And we're looking at phi scattering, okay, in the effective field theory. So we must be below this energy m, no? And my cross-section starts at energies at least twice the mass, okay? At energies smaller than twice the mass, you don't have anything happening, right? There we took the mass to 0, but who cares? Let's put it back, okay? So nothing happens, and then it increases, and for a while it's described just by the n to the 0 here. So no box, just phi to the 4, okay? This is a constant. The amplitude is a constant. The amplitude square is also a constant, so it goes like this. And then at some point, you'll have the guys with derivatives that become important, and then at some point you will see m. Sorry, let me do it a bit more like this. Okay. So in here we don't care. I'm fuzzing it out so that deliberately, not accidentally. Yes. The vertical axis is just a placeholder for where m, the b, s times sigma, the cross section. So it's basically amplitude square. Well, no, I want s times sigma because I want to insist on this thing, that there is no dynamics below 2m, okay? So the cross section starts only at 2m. The amplitude not. The amplitude would keep on going constant here. But this is a fact. So good, let me show you here what it means to be relevant or irrelevant, okay? So in this part, we are dominated by the kinetic term and by the interaction, phi to the 4, okay? It's a constant, you can compute it. In here, we start being dominated by phi squared, box squared, phi squared. It increases with energy, okay? And instead, down here, interestingly, we are dominated by the most relevant of this guy, phi squared. This has delta equal 2, which is smaller than 4. So it's the most relevant operator in our theory. At small energies, you just have the mass that freezes all the dynamics and nothing happens, okay? So this is a delta equal 2. This is delta equal 4, so the limiting case. And this guy here is a delta equal 8, actually, this phi squared, box squared, phi squared. Yeah, good question. The box turns out that gives you S plus T plus U in the amplitude. S plus T plus U is equal to 4m squared. So it's just a kinematic accident that the box does not give you anything extra, okay? There is another way to see this within the effective field theory, that operator can be eliminated. But it's not so important, to be honest. You don't need to eliminate things. Good, so you see, marginal, good at high energies, but at low energy doesn't do anything. Sorry, irrelevant, marginal, yeah, the central part, and relevant here, okay? Good. So there is a crucial thing that I used to draw this picture, which is the fact that I know the coefficients here. Here we have m squared, and here we had mu squared over big M to the 4. So this is much smaller than whatever, 1 of the energy squared, just to give it some units. And this is much bigger, much smaller than big M squared. Because the coefficients take these values, we have distinctive regions here. But now let me show you an example that I find cute, which is which will teach us the following, well, will answer to the following questions without knowing anything on the coefficients, on the GN. How predictive is the effective field theory? Okay, and let me give you the following example. Okay, we have an experimentalist. There were 2 in the audience that measured a certain cross-section, whatever, as a function of the energy. Is not the same. I mean, whatever curve we can do. So you measure this thing, but we measure it so precisely that it's a function. It's a line, okay? And we measure it. Sorry. We're measuring up to an energy Emax, okay? So this function here is a experimental data as a function of energy given to us, okay? And now we want to ask the question, what is the theory? Behind this? Okay? So I will make it a bit simplified. And sorry, I'm using this space as well. So, and with theory, I identify the theory with a set of monomials that are used to approximate this function in the following sense, that so this set is a basis to approximate this experimental function, and defined as follows, that sum of some coefficient times the powers of n minus my experimental function of E is always smaller than epsilon, so there are for all epsilons, so for all levels of precision, I can always approximate with this basis the function experimentally very well, right? This is the set of all the operators, right? Operators with all powers of energies are allowed in this basis, okay? This is called the Weierstrass theorem, that monomials are a basis of this time. Now let me ask you the following question. Of the following examples are also good bases. And let me give you a few examples. So which of these is also a good basis to approximate our experimental data? Do you still have the QR code, or I have to flash it again? So if you want it flashed again, raise your hand. Okay, let me raise. Sorry, wait, I have to clear the responses from before. Okay, good. Right. The third, sorry, is e to the n factorial. Yeah, I was a bit lazy, I didn't write the whole thing. But it's e to the n factorial. Right. Okay, I'll remove this. No. Okay, let's assume you have all thought deeply about this question and see what the answer is. Good, an almost flat distribution, fluctuating fast. That's exactly a sign of being on the, well, okay, you see what it is. The right answer is, sorry, I forgot. Yeah, the first one. Well, you make you're fitting to a structured data set with, good. So there is a theorem that I like very much. Maybe it's completely irrelevant, but I like it to show this very problem, which is the following. It's called the Munzatz theorem, and it tells you that a basis of this type, e to the lambda 1, lambda 2, lambda 3, and so on, it's a basis if and only if the sum of 1 over the lambda I is equal to infinity. So this tells you that you don't need all the guys to make a basis, right? So, of course, you can fit this curve with all the guys, but you can equally well take any basis that skips as many as you want, right? This goes like 3n. 3n diverges in the sum, okay? This is n squared, it converges, and factorial converges. So you cannot skip too many, especially at infinity, you need quite a lot. But you can skip a lot. This means that asymmetry is not yet enough to make the effective field theory predictive, because I would not be able to tell apart the full theory from the symmetric theory that kills 2 every 3, okay? You got the message from this nice example? And the Munzats, I kind of like it. You don't expect this, right? That you're it's like, because we're used to vector spaces defined by a finite dimensional vector space, right? And there, if you miss out a piece in the basis, that's it. You're not going to be able to reproduce that bit of the basis with the other guys, okay? In R3, if you remove the y direction, the other guys cannot match up. But in infinite vector spaces, like defined by the set of functions here, you can do this, okay? So I kind of like it. Yes? Yeah. Exactly. Yeah. Exactly. No, you're so an operator with positive bigger than delta will go like will go like lambda lambda to the delta minus d, which is positive, right? And then we go to low energies, and in the infrared, when energy goes to 0, this goes to 0. So it's correct, I think, what you're saying, right? Right, but this is how the whole operator rescales. This operator will go lambda to the delta, right? And then the minus d comes from this guy, from just the measure here, right? Okay, so this is a complicated way of telling you that symmetries is not enough. Okay? And in fact, what we need is just a simple we need also a simple information on the coefficients. And in particular, we need, like we had in the picture before, right? That we knew the coefficients of these guys, roughly. We knew that one was smaller and the other one is larger. So this information is called power counting. Okay? Power counting it's a minimal information that basically tells us what operators we must keep and what operators we can neglect at a given energy, okay? So for instance, in many reviews on effective field theory, you will find that these coefficient will go like order 1 things divided by appropriate powers of the energy scales. this is just a possibility. Power counting depends on what theory it's coming from. Power counting depends on the full underlying dynamics, but is a minimal piece of information that makes it all the way to the effective field theory. So in this course, I'm not going to go very much into this power counting. The only thing I'm going to tell you is that we're going to use power counting just as a rationale to say what terms we focus on in the Lagrangian and which ones instead we assume to be small because they're suppressed by more powers of m and coefficients that don't get too large, okay? So in this course, the power counting tells us what operators we keep and which one we kill, okay? All right, so this power counting is the third ingredient of our effective field theory. Okay, so we need power counting, symmetry, and particles. Okay, yes. Fair enough. Power counting is a piece of information that relates you to the UV. And you cannot live without that. Very often you hear that effective field theories are very good because they are model independent. It's not entirely true. Without the power counting, there is no model independence. If you think that it's model independent, it's because you're making some model dependent assumptions and you're not telling them. So the power counting, which is just telling you, for instance, yeah, I'm keeping these 5 terms and then I'm neglecting the other ones, it's an assumption about the UV. We will see that there are symmetries that kill the first guys and maybe start at the 7th term, right? So in your power counting, you're killing this very theory that I've just phrased. So you need this. Yes? Yeah? If you're developing a model completely bottom-up, you mean? Yeah. Good, exactly. That's you're putting in this information. So you have it. I know it's hard to accept. Like I also went through a moment in which I know this is, but it's a truth. I mean, eventually, in this course, I'm going to try to develop things as much as possible from the bottom up. But there will always be an assumption about what we neglect that is hidden in this power counting. So keep an eye on the effective field theories maybe you come across in your life and ask yourself, yeah, what was the power counting there? And there is always one. For instance, in gravity, when we, gravity is an effective field theory that describes gravity below the Planck scale, we are saying that we are operating at energies much smaller than the Planck scale, which is where we believe this theory to stop being valid, right? And we are also saying that that theory doesn't produce anything with a coefficient which is 10 to the 19 accidentally as to compensate for the suppression in the scale. So we're putting in an input. Yeah, let me finish here. I could go on a little bit more, but maybe we can discuss this over coffee. Good. So 3 ingredients. And in the rest of the course, I'm going to mostly focus on setup that delivers already 2 of these ingredients. And these are Goldstone bosons. So Goldstone bosons are particles that originate when we have, let me insist on this picture, we have a symmetry G that is broken at some scale into another symmetry, H. Okay, so we have G being broken to H. And so who here knows Goldstone theorem? Hands up. Maybe who doesn't know it? Okay, let me, yeah, it will take a while. I'll just tell you what it is. A proof, maybe we can do again over coffee or beer, or instead of the match tomorrow. So this is a group. It has a certain dimension. For instance, SU2, right, has SUN has n squared minus 1 generators, and this is the dimension of the group G, if G is SUN, okay? And so when the symmetry is broken, Goldstone theorem tells us that there will be massless particles and their number is given by the dimension of G minus the dimension of H. So for every symmetry that is broken here, you could have a massless particle. Caveat, I'll put a smaller equal. You probably have not seen this before. We will see in a couple of days why. But in general, for many cases, it's equal, but sometimes it's smaller. Okay, let's be ambiguous here. But the classical case, it's this one. So we have a symmetry. Sorry, I'm just flashing this through. We have a system with a potential that is invariant under rotations. This is a U1 symmetry as rotations along this axis. And there is a state that breaks this symmetry, and in the theory that emerges, there is one massless particle. There is the fluctuations around this bottom of this thing. I'm being a bit fast because there are so many beautiful things that we should discuss, and maybe I'll leave this a bit faster here, okay? Is it okay? No proof of the Goldstone boson? Okay. So let me stick to this idea of Goldstone bosons because of Goldstone theorem, we obtain particles. So there is a notion of particles with massless in this picture here. So we have particles that live automatically here at m equals 0. And in this structure here, there is the idea of symmetries. Two types of symmetries here, G and H. So this was requirement 1, defining our effective field theory, and this is requirement 2. So Goldstone boson automatically deliver a situation in which we have massless particles, so we have a mass gap, and we have symmetries, okay? So I'll jump to the prototype case of Goldstone boson, which is pions. Maybe some of you have already seen pions. I remember I used to find them pretty boring, but now I believe they're spectacularly interesting. Maybe I became a nerd on this, but there are so many beautiful things. And at the beginning, I thought I will take another group and make it a bit more exotic, but actually, it's just so instructive that maybe it's worth thinking. Even if you have seen them, let's talk about them again. So, pions. The idea is that in our picture here, we have QCD, which is described by a Lagrangian that you have seen this morning, and I'm writing in a slightly different form. So this is what Julia had this morning, with a trace or whatever. And here, these QLs and Q right, they are vectors that include the quarks, up, down, strange, and so on. Okay? Yes? It's -1, and then there is a trace that I forgot. So it's -1/4, and then, well, let me do this, whatever, trace, yeah. We're not gonna look at this anymore. You can omit it from your notes, and Julia will will be outraged. They disappear for me. They disappear at low energies. So we have. So what happens is that, as we mentioned before, if you study the coupling in QCD, it's very weak, and then at some energies, which is roughly 1 GeV, the coupling becomes strong, okay? And basically, this transition from QCD to whatever lives here at lower energies is not known. It's impossible to compute. So what we know is the following, that the Lagrangian of QCD has a symmetry G equal S, U, and F left. So you can rotate these matrices in the number of flavors. There are NF of them. And you can rotate to the left and the right independently. But because this guy comes in with a dagger, right, if this rotation is within S, U, and F, well, also U and F, but let me not go there yet. Basically, the transformation cancels out. So this is a symmetry of QCD, okay? And in what follow, I will take NF equal 2 today, and maybe 3 tomorrow. The reason is that there are some mass terms for the quarks that have this form, but I will ignore them for the time being. Today I will ignore them, maybe also tomorrow, and maybe also after. Julia also said it. We can, at colliders, ignore them. So we're safe. As long as we work with the first 3 guys, we can neglect these things at energies, because the mass of the strange is 100 MeV. This is 1 GeV, so you have a certain gap there, okay? Anyway, let's ignore this mass there. So what else do we know here? Well, there's another thing that we know, which is that at lower energies, the symmetry is no longer this one, but it's S, U, and F, or in the case, and SU2, diagonal. So meaning where the transformation of the left and the right is the same, okay? In that sense, diagonal. So this is preserved. How do we know this? There are 2 ways. First, you look at the spectrum of particles here at low energies, and you find that roughly they fall into multiplets of this diagonal group. And secondly, there is another piece of information that maybe we shouldn't use too much, but is the fact that it's roughly what happens here is that there is a state, an operator, which is the product of these two Q left and right that becomes different from 0. And this, if you act with a transformation left equal right, this thing is untouched. However, when L is different from right, this is broken. And when L is equal to right, it's preserved, okay? But for us, it doesn't matter so much what happens there, okay? What matters is that we have G and we have H, okay? Now, when we count the sizes of these groups, G, I mentioned to you that somewhere SUN is n squared minus 1 generators. So when we look at SU2, there are 3 generators here, 3 generators here, 3 here, and therefore there will be 3 Goldstone bosons. And these are the pi plus, minus, and 0, okay? The pions that you might have come across later. So in this picture here, we have at low energies just the pions. I write them 0, 1, 2, and up here you have QCD. So as someone in the audience mentioned before, yeah, how do we build now? So how do we, sorry. Now the goal is to be able to write a Lagrangian for the pions to describe what happens here at low energies, okay? And the only thing we know is this, that the symmetry was broken in this way. And the problem is that we want to write a Lagrangian for the pions, but this Lagrangian must be G invariant. Okay? Because it has to respect the fact that it comes from a theory in which G is a good symmetry. So now, these pions transform in a very complicated way under G. Well, I don't know if these words exist, but whatever. So let me give you an example in which this is not the case, which is the one we had before, the Mexican hat, okay? In the Mexican hat, we had a U1 symmetry that is broken down to nothing. And here, the pion is the degree of freedom that lives around this valley. And when you make a U1 rotation, you're just shifting the thing around the valley, okay? So in fact, this ring, the G over H here, is isomorphic to the line R is flat, and the pi goes just to pi plus a constant here, okay? Now, for cosets of this type, this is totally not the case. Let me give you a slightly different coset, but that it's very similar to this one, but maybe that you can actually understand what goes on. And this is the SO3 broken down to SO2. So this is simply a sphere. SO3 are the rotations on the sphere, the 3 Euler angles. So, and we break it by the existence of some object, an arrow pointing in one direction, okay? So in this case, there is still a symmetry, which is rotations around this axis. And this is the unbroken group H. Now the pions here in this picture, they are pi1 and pi2. The 2 directions perpendicular to the arrow, okay? And G, SO3, is a rotation in one of these directions. So for instance, let me make a action of G here. Pi1 shifts, good. However, another direction, which is maybe here, will shift, and then it will get distorted because the sphere is fatter at the belly than it's up there. Similarly, another vector here will come here. So the transformation of this vector is not just a shift. It's a shift that gets pushed a little bit along pi2, okay? Right? Do you see how it goes? Try to draw it. There is always a drift towards a different direction. And this means that the pi I, they don't just get moved to the pi I plus c, well, where's ci, but there is also a nonlinear piece, which is related to the pions themselves, okay? So depending on which direction you're pointing, there is a nonlinear interaction due to the fact that the sphere is a compact object, okay? So we don't need to dwell very much into this, but it's just to say that the transformation is complicated here. So it's very hard to sit down and compute and build a Lagrangian that is invariant under a transformation that is complicated. So there is an object which has simple transformation properties under G. And I will write it over here. So this object is it's a matrix. This is these TAs here are the broken generators. And these objects, if you can just accept that this is an object that contains the pions, or I can give you two explanations of how you go there. So the state that I advertised before, this vacuum expectation value of Q left, Q right, these can be seen as parametrizing a VEV times this matrix. So these would be fluctuations around the VEV, and so it's the state made by Q left and Q right. Yes. F is just a constant. So, okay. Sometimes it's written F pi, but I'll just write F. So the this U parameterizes the fluctuations of this state. The state gets a vacuum expectation value, meaning that when you measure its average, it's a number, but then it fluctuates here and there. And these fluctuations are captured by this state here. Yes, this mean. And the exponent, no gamma 5. No, this is really a, so the indices here, I and, well, sorry, the spinor indices, alpha and beta are contracted. So with these two guys. So it's not a spinor matrix, but it's a matrix in flavor space. So this is A and B, and these has indices A and B, where the A is like U, D, S. So it's really in flavor space. It's an extended object. So right, and the way this transforms under G is simply because it comes from this guy. This guy is transformed with a left and a right. So this one also transforms with a left U and R dagger. Well, yeah. Okay. So it's a simple transformation in G. But hides a complicated transformation on the pi. Now, when you apply an element of H, this thing transforms. So H is defined by the fact that left and right are the same. And what you find is that your U, you have left U, if we call this H for later definition, transform like this, but now we can write this as a series in X. Okay, so we can put the H here and HD here, and sorry, H dagger. But because H and H dagger is 1, it's an element of SU2, we can rewrite this as H dagger to the N. Okay. Therefore, the pions transform linearly under H. Meaning H times pi A T A. Okay. This is a linear transformation, like a rotation. Okay, so the important thing is that pi transforms badly, but G transforms simply. So let's build now the Lagrangian that contains this object U and see what we can do. So we want to build a Lagrangian out of this U, okay? And right, let's see what let me ask you. what we can put here. So, right, we can put, I'll write some terms, and you tell me which one you would like to put. So which one do you like? Let's see. Wait, don't. Okay. Yeah. This one? Yeah, these are matrices. So I just call them H to denote the combination, right? They are the same, I call them H. So now we act in this way, but with a member, with an element that satisfies this thing. So you have H on the left and H on the right. Doug? Sorry, this is matrix, matrix, matrix. They're all matrices. So this is a matrix in SU2, this the diagonal piece, because it satisfies this thing. That one as well. And this one happens to be also matrix in SU2, but it actually lives elsewhere. It lives in this G over H factor, but it's still in SU2. So it lives in SU2 cross SU2 without SU2. And right, and then you can see how the transformation from the U transfers to the pi's, and you see that the matrix pi A TA transforms with the sandwich. And remember, it's like a rotation. So yeah, you can rewrite this as just the pi A rotating like a normal rotation. Thank you. All right, I assume in the meantime a verdict has come. Let's see. Yeah. In this form here. That one. So maybe here, if you accept that this is just a fluctuation of an object like this, that contains the pions, yes. However, there is a much more systematic approach, well, a more systematic approach that I will show you tomorrow, hopefully, in which it turns out that this is the only way, well, I will show you which is the only way of writing it. But maybe if you don't like this, let's put it this way. You can try to write down a Lagrangian with just the pi's. You write the kinetic term, d pi, d pi. And then you apply a G transformation. You're not going to get the whole transformation right because it has all these nonlinear terms, but you can split the first non-invariance terms, right? And then you can, in this way, you can build your Lagrangian terms to terms. And after a while, you repackage it and see that it is the answer of this quest. A priori, right now, you don't have a reason to think that the pions can only appear here, maybe. What motivates you is that this is an object with a simple transformation, but you don't know if it's the only one. Okay. So, good. What did you guys respond? Okay, most of you went for this guy. It's correct. And the reason is that, well, this guy is 1. U dagger U is equal to 1. So this, you don't have it in the Lagrangian. And this guy is not invariant because it doesn't transform in the correct way, okay? So it's this one. Give me just 30 seconds and I'll... So good. So we have that our Lagrangian The first term is that one, which I write with a normalization, squared delta mu u dagger, delta mu u, and the trace. And we can expand this, okay? I'm going to do it for you. We expand it in the pi's. We take the traces, and what you find is a kinetic term. Good. And then there are other terms that are related to this. The next one is this one. Okay. And then you have order delta pi to the 4. Okay. So I'm expanding and I'm getting this. And now let me just the last thing so that we close on the actual culprit. This is the first term that we can write down, okay? But there are more. And in particular, so let me erase here, there. In particular, there are things that, for instance, a square of this type of thing, which is delta u, u dagger. Well, let me not put the indices, so I'm a bit faster. And many more. But you see, this one has two derivatives. It's of order delta squared, and this one is of order delta 4. Okay? This one will imply that the observables that come out of these terms have two more derivatives, so two more powers of momenta or energy when they make it into an observable. Now, it's where the power counting comes in, okay? So, power counting, I'm assuming that, that these have the form of, they're suppressed by a scale, lambda QCD, which is of order 1 GeV, as opposed to the guys here that instead are of order 1 over f squared, and f here is about 100 MeV. So 10 times smaller, meaning that this term is larger, okay? So this is the power counting in QCD, which lambda QCD much bigger than f, okay? And for the purpose of this talk, this course, it will imply that basically we can say goodbye to these terms. We haven't thrown away everything because here, this is the kinetic term. This guy is a quartic interaction between 4 pi's, and then, sorry, here there was a 6th, and this guy is a 6-point interactions, and they are all fixed. Okay? So the effective field theories that we've been building only out of symmetry is an incredibly rigid structure under this power counting that kills these terms and allows only this term here with a lot of nonlinear interactions. And we will see that, well, that's it, basically. Very rigid theory, very predictive, although it's a shitty effective field theory that in principle has whatever you want, okay? Good. See you tomorrow. Well, questions, if you have.
Any urgent question now? So we have a coffee break and then session, the Q&A session that is not going to be a Q&A today, but please come back.